Okay, we're recording now. And we're going to go through the session 5 lab on the needle sharing data set. So I'm going to start with this code. I'm not going to redo, it takes a long time, the data loading and recoding. So I'm just going to run this. First of all, make sure I'm in the right directory with sessions, set working directory to source file location. And then I'm just loading tidyverse so that I'll have readr and dplyr. I should note this dplyr double colon is unnecessary because dplyr has overwritten a filter from the base package. I just sometimes do this because there is another filter function in base R, and this just makes it clear that I'm using the one from dplyr. So I loaded the needle sharing data set, called it needledat, and then I filtered it for rows where sex was either M or F, ethnicity was either white, AA, or Hispanic, and the homelessness variable was not missing. And then using mutate, I recoded homeless so that 0 was no and 1 became yes. And because I put no first, that's the reference factor with recode factor, which is from the dplyr library. And I recoded HIV with 0 negative as the reference category, 1 as positive, and 2 as yes. I'm actually not sure now what the difference between positive and yes is. Does that make sense to anyone else? I'm just going to take a look at that summary needledat HIV. There are only 2 yeses and 11 NAs. I have no idea what that means. I would be almost tempted to just call 2 positive as well.
Is there any way to go back like we did with the COVID and
Go back to the original publication.
yeah, back to the original publication and see if there were 2 that did anything?
Yeah. Yep. That would be the way to do it, to go back to the publication and see if they reported 8 of something and 2 of something, if they explained what the difference was between these. I'm pretty sure that neither of these would be negative.
I have like a little bit of a sidebar question about this.
Mm-hmm.
When you use the mutate function and you have, first you say HIV equals recode factor, and then you're using HIV stat,
Mm-hmm.
is that, are you renaming that? Are you renaming HIV? What is the HIV
No,
referring to again?
I'm creating a new variable called HIV.
Oh, you're creating the new variable called HIV, which was
Yeah.
previously called HIV stat.
Right.
Okay, I was mixing
So
up.
HIV stat would still be there. I'm just creating a new factor variable called HIV.
Right. Okay. Okay. Yep. I just mixed that up. All right. Thank you.
No problem. I mean, so if I did this, then I would see those just recoded as positive. And maybe I'll just stick with that for now. So compare the mean to the variance of the outcome variable and calculate what fraction of the counts are 0. So I can use the summarize function for this. That's from dplyr. Summarize to mean equals mean. I'll put this in. I'm not sure if there actually are missing values there. Let's see. Summary needle that to. Yes, there are missing values. So I'll leave that na.rm equals true in place. R equals do that first. Okay, that's working. So we can see already that the variance is it's about 30 or 40 times higher than the mean. So clearly it's over dispersed. Now I'm also going to calculate the fraction of zeros. So frac 0 equals.
Is there a variance? Is there like a point where you make a decision whether it's over dispersed or not, or is it but just kind of by guesswork or assumption?
I mean, this is a qualitative assessment. I mean, if you wanted to do this quantitatively, what you would do is compare a negative binomial regression to a Poisson regression. And if the negative binomial is a better fit, then that's evidence of overdispersion. This is kind of in the category. Okay. This is kind of in the category of the diagnostic plots, in that it's more, it's more to give you an intuition about the data set, and I think it's a more something where having experience with multiple data sets will help, and where doing this will give you a better intuitive, this is exploratory data analysis meant to give you an intuitive understanding of your data more so than a regression will. So, if you see something where the variance is twice as high, that's obviously not as overdispersed as something where it's 30 times as high. But yeah, I'm intentionally avoiding here doing a statistical test on this, as I often do with the exploratory data analysis and assessing model fit. It's, I think, not just me either, that most statistical analysts will avoid using statistical tests in order to tell them if a model fits, or when doing exploratory analysis of the data set. So, but this is clearly a lot of overdispersion. So the fraction of zeros is going to be sum shared equals 0 over one thing I could do here to make things easier, since I'm having to account for these missing NAs at every point, would be to get rid of them to begin with, such as filter needle dat2 not is.na shared SIR. I could have also used the complete cases command to do that same thing. And then just go like this. And then I can get rid of these because I already know there are no more NAs in this column. Length shared SIR. I think that should do it.
Length shared SIR or SYR is just the number of rows, like the number.
Right.
Okay.
Yep.
The number of
Yeah.
people that they asked whether or not they shared syringes.
Right. So
And
I
you're
could
just
have
trying
also
to find out what how many of the total didn't ever.
exactly.
Okay.
So I could have instead used nrow or something here. I think I could also use, is it n? Yeah, that does the same thing. So it's telling me that 77% of the participants never shared a needle during the study. And then actually down here, I used some inline R code to summarize these. So actually, I'll create this. So I've just written these to a variable called mean var zeros. And then I actually, using these single ticks here, this is a way to put results in a paragraph in our markdown without actually going and writing it in manually. It's kind of a nice way to discuss results and make sure that they are up to date if you update your data set or your analysis. So who's following along so far? Nice.
Yep, following.
Yeah.
Great. Okay. Create a histogram of the outcome variable. This was done in the lecture using base R. Let's do it here with ggplot2. All right. Note the filtering of complete cases only is unnecessary because ggplot does it anyways. But this gets rid of a warning. Okay, we'll try it without filtering. Specifying the bin width is also unnecessary, but by default, it creates bins of size 2 with 0 and 1 in the same bin, 2 and 3 together. Okay, well, let's just start with a fairly stock ggplot2 histogram. So it's going to look like ggplot, it's needle.2, AES is X equals shared syringes plus geom histogram. That should be enough to get a basic plot. So there's that warning that was mentioned and that hint to pick a better value. And there's our histogram, which looks not too bad. Let's try it with bin width equals 1. So this, right, is putting 0 and 1 needle shares together into one bin, which isn't ideal because it's not separating out those who never shared a needle from those who shared a needle once. So there it is with a bin width of 1, and you see that this, as we saw before, this fraction who never shared a needle is much, much higher than those who shared a needle at least once. And I could here, if I wanted to get rid of this warning, I could do like before, start with this filter. It's really, no, it's not necessary, but and it would just be like this. But it will look exactly the same. Okay, let's see, fit Poisson and negative binomial models as in the lecture, with and without zero inflation. So let's see, I actually have the lecture notes on hand to help me a little bit because that's too much memory for me. So we did Poisson using base GLM. Okay, just take a look. So there's the output, see some very strong associations with sex, Hispanic ethnicity, and homelessness. And so sex female is the reference group for sex. AA, African American, is the reference group for ethnicity, and not homeless is the reference for homelessness. So this negative estimate here is saying that men have a lower rate of needle sharing. Hispanics have a higher rate of needle sharing, and homeless people have a higher rate of needle sharing, according to the Poisson model. So I'm going to copy this over just to save a little typing here. And we need the mass package here. And this was, what is this? glm.nb. I no longer need this family. That's all I need. Now I can take a look at this. So this actually looks very different now. Homelessness is the only predictor that remains significant here. Really different results. Certainly doesn't inspire that much confidence in those previous results. Let's try the zero inflated Poisson model. I'll start again with this, just to save some typing. And I'll call this ZI plus. And then here I just have to do dist equals. No, I got something wrong there. Okay, now what I see here, I see two full sets of regression coefficients, one for the count model and one for the zero inflation model. And as I've mentioned in the lecture, this default of fitting a full model to the zero inflation component, I'm not a big fan of. This is a very complicated model where each of these two contributing components to the mixture involve all of the predictors. And it also makes these rate ratios very difficult to interpret because the actual rate ratio for predictor, say sex, is determined by both components of this model. So unless you have a reason to think that is justified, that complex of a model, I prefer as a default using an intercept only model for the zero inflation component, which is what this pipe 1 does. So if I do this and then take a look at my summary, now I see only an intercept for the zero inflation component. And this is telling me, so this is a logistic regression, and this is telling me that the log odds ratio for this for a zero is 1.221. So this predicts a constant probability of everyone in the study of being a zero, and then if it's a non-zero, this count model predicts the number of counts. And this significant p-value is just saying that we have evidence that this estimate is not zero, that there is evidence of zero inflation in this mixture model.
So this is kind of like a more complicated way of just dichotomizing between ever and never.
Well, it's saying that I guess you could put it that way, but it's saying more or less that there are two different processes at work. It's saying that there's one process that determines whether someone ever shares a needle or not. And then if they do share a needle, there's another process determining how frequently they share a needle. Whereas with the plain Poisson model, there was just one process determining the rate at which someone shares a needle.
Oh, okay, okay.
So this zero inflation component saying that there's one process determining whether someone ever shares a needle or not, it might make sense to put some of the covariates or predictors into here, such as if we had a variable for like whether someone shares a household with another user of injection drugs, that would probably be a strong predictor of whether they ever share a needle or not. And it would probably make sense to put in the zero inflation model. You might also hypothesize that whether someone has HIV is also a predictor of in this zero inflation model, predicting that someone who has HIV for that reason is less likely to share a needle. So that's relatively easy to add if we just want, a partial model here. I could just add what is it called? Call names needle that to HIV. So now I have actually a predictor in the zero inflation model that is not a predictor in the count model. So these can be different models. Turns out I didn't see evidence of HIV positivity being a predictor of zero inflation. See what happens if I add it here. It is a strong predictor in the count model and predicts an increased rate of needle sharing, or an increased rate of the number of times a needle is shared. All right, but that wasn't part of the question here. So you can substitute that with another variable to add it to the count model and use regular model formula syntax to create any count or any zero inflation logistic regression model you want, or omit the for a full zero inflation model. Okay. Okay, now finally I got ahead of myself there. So that belongs here, the intercept only CA model. This is like that. So this is a Poisson model. And now let's do, I actually didn't include it here, but let's call that full. And let's do negative binomial model. Okay, let's take a look. So again, like before, whereas we had all of these different significant associations in the Poisson model, in the negative binomial model, it's only homelessness. So that's kind of the only one that I have maybe a little bit of confidence about. We could do that. Make a box plot of needle sharing by homelessness and other variables, I'd say predictors. So that's going to look like ggplot2, see if I can do this first try on ggplot2. I usually use base graphics myself, but I do like ggplot. So this is going to be needle dat2 AES X is going to be homeless. Y will be shared syringe. And then let's just do geom box plot. Oops, sorry. Okay. So you can kind of see it's a little bit hard to see just because this is so extreme here, but you can see how the third quartile, both the first quartile, median, and third quartile are all 0 among the non-homeless, but among the homeless, the third quartile is 1, and we have more spreading out. What is the fraction of each of these though? Table, needle, dat2, homeless. Okay, it's about equal numbers of homeless and not homeless. So that can produce a misleading box plot. If you have one group that is much larger than the other, then you'll tend to see more outliers in the larger group just because you're seeing more of the distribution. But that's not the case here. They're about the same. So that's what this difference looks like. If I wanted to do this for another one, let's say sex. Yeah, that really doesn't look, wow. There are some more up here, but it's a little hard to say anything. And ethnicity. Yeah, there is a difference in the quartiles here. One thing I might want to do, let's take a look at the help page for geom box plot. Var width is use var width to show the sizes of the groups. I'm just going to do var width equals true. I could add these notches. I highly doubt they're going to be informative. The notches are like a visual hypothesis test for differences. I think the var width is the most useful thing here. So now you can see that Hispanic is the smallest of these three groups because it's less wide than the other two. So maybe it'll be interesting to see later whether it looks like there's any collinearity between Hispanic ethnicity and homelessness in this group. We could do that now since we're on sort of on the exploratory data analysis part. Why don't I go down here and assess whether there's maybe any multicollinearity and bring that up. Okay, so my trick for multicollinearity is to create a model matrix. model dot matrix, and I'm going to do it just like I did here. Data equals needle that 2. Let me see if I got that right. Yes, I did. The nice thing that model matrix does for us is it recodes the factors as dummy variables. And so the entire matrix is numeric. And I can also have together here categorical variables and numeric variables. If I did have a numeric variable in here, then I would just have a column that was numeric here alongside these dummy variables. So I'll call this MM. Now I can make a heat map, or I can just make a dendrogram. I can make a dendrogram without any additional packages. I can just do, for example, let's see, core MM. Yeah. Well, just by doing correlation of MM, this gives me correlations already between these variables. So I see a negative correlation between ethnicity white and ethnicity Hispanic. That makes sense. I see a positive correlation between homelessness, yes, and sex, male. And I see a small negative correlation between homelessness and Hispanic ethnicity. So multicollinearity does not seem to be an issue between this sort of weak association with Hispanic ethnicity and the stronger association with homelessness. And also a small correlation 0.15 between white ethnicity and homelessness. So I can do that. I can also do, I can visualize it. I can do, let's see, I think, can I just do, I can do something like 1 minus the correlation as dot dist. And then need to get rid of the intercept at some point. I'll get rid of it there. Okay, that looks like a good distance matrix. I can do hclust, and I can plot that. So here you see male, sex, and homelessness as being the most closely associated variables. It's just sort of a visual exploration. And the nice thing about this is it can extend to any number of variables. Another way I can do this is this pHeatMap package just is an easy way to make heat maps. And then I can go pHeatMap mm-1. So this is a plot of each of my variables, and again showing, let's see, showing some relationship between homelessness and male sex. What had I determined that to be? That looked like male sex and homelessness. So that was, well, maybe that's easier to look at just as the correlations. Male sex and homelessness, that was the correlation of 0.17. And then the other largest, well, that was the largest positive one. Also between white ethnicity and homelessness, and you can kind of see that here too. But there's no really strong multicollinearity in this data set.
Thanks, this is really helpful.
No problem. Yeah, this is kind of an exploratory thing. There are also statistical methods of assessing multicollinearity. You can use this variance inflation factor. I forget right now which package that comes from, but you just apply, it's called VIF function to your fitted regression model, and it'll estimate for you how much the variance or your standard errors are inflated by multicollinearity. But that again kind of depends on your model. And it also doesn't tell you where the multicollinearity exists. So I really like these methods just as a visual representation of where multicollinearity appears to exist in your data set. And it's great too when you have a bunch of variables. Like I could actually do this for everything in the data set. Let's do this again for instead of just these three, I can do it for everything. Oh, what happened? I must have the standard. Okay, I have something that is all zeros or only one. Let me see. I need to do a summary of needle dat2 and get an idea of oh, I need to get rid of this ID column. Let's just do minus ID. Let's see if that works. And I might as well, I'll get rid of the intercept call names, the intercept right away. -1 gets rid of intercept. What is still wrong here? Summary. Oops, I can get rid of this now. Maybe I'll do apply MM2 and var just to see which one has a variance of 0 and sort. Okay, so this has 0 variance and I'm going to need to get rid of it. So I'll get minus this sex abuse also has a very small variance. Let's see what it looks like. Table needle dat2 sex abuse. Okay, it's not that small there. 17 yes and 100 0. So I'll leave that in place. There, now I'm getting a plot. So what is this? Square root NIVD and square root NINJ. I don't know what all of these mean, but they're somewhat collinear. log share syringe, shared syringe, and SHS year. So these are obviously all some kind of measure of syringe usage, and they're closely related. So that's not surprising. We have another group over here, ethnicity white, DPRSN diagnosis, depression diagnosis, and HPLSNS. I don't know what that means, but it's related to depression diagnosis and white ethnicity. Over here we have Hispanic ethnicity with polydrug. I don't know what that means. But if we wanted to then actually see, so, you know, this is a qualitative thing here, this, you know, this plot, but if we wanted to compare two of these, so let's look at these two. I can go with needle dat2 table Hispanic and polydrug. What did I do wrong here? ETHN. Call names. Oh, that's because, right, because this is in the model matrix. So that was not one of the original ones. So call names MM. Make sure I get this right. Right, so this is with MM. So actually, I'm going to go back here and instead just use ethnicity. Okay, so here we can see this polydrug variable, which has values of 0 and 1, and ethnicity. And it looks like it's about 5 times more likely to be 0 in African Americans, about 7 times more likely in whites, and only 2 times more likely in Hispanics. So going back to the original 2 by or frequency table, that's what this level of collinearity looks like. And I could do the same for sex and age. Sex, age. So it's a little hard to see here because age is a continuous variable. So instead, let's do a box plot, ggplot, needle dat2, AS, x equals sex, y equals age, plus geom box plot. It's not too much. You could also look at a like a t-dot test, x equals sex. No, that's not going to work. How do I'll do it. Age, sex, data equals needle dat2. It's not even significant. That's kind of interesting. Let's go back to this. So one thing actually that I can note here is although these are together, the further down on this, the further down on the height, the stronger that association is. So even though these are together, they're fairly high up on the height level. I want to see what the actual correlation is because this was based on correlations. So I can so this was between sex M and where's age, 0.51. That is a pretty high correlation, 0.5189. But it doesn't really translate into the box plots or the, yeah, I mean, you can see it a little bit in the box plot, but it's not much. So it's worth following up on, these. It's not a perfect thing. I could also do this. This might be a little bit clearer in the pretty heat map. Actually, I can get rid of the -1. So I get everything. Let's see. Yeah, so actually on the heat map, age doesn't look very associated with anything. Some of these other things, these square root things, look closer. Part of the difference, let's see, if I look at the help page for P heat map, I need to be reminded of how it does the clustering. Boy, a lot of options. Right, it's using Euclidean distance, whereas we were using Pearson correlation. So actually I could replace that with correlation. Clustering distance calls equals correlation. To see how that looks different. Oops, sorry, put that in the wrong part. That belongs here. So that certainly changes things. Now we see that correlation between age and male sex. So Euclidean distance is actually a sum of square root of the sum of squares. Makes sense that they would not be similar on that measure, but that they could still be more similar on correlations. I'll do this for rows too. So the strongest correlations I see are between HIV stat and HIV positive. So that makes sense. Also see something fairly strong between NIVDU and square root NIVD. So that makes sense too. That's just the derived variable of the same variable. And between shared syringe and log shared syringe also makes sense. All of the very highly correlated variables are really just the same variable. And then the other ones exist, but they're not as strong. Maybe I'll copy this up here too. Okay, so use chi-squared nested deviance tests to assess which model seems to be the best fit. So I want to calculate the log likelihood from each model. And the simplest way is to call the log-like function one at a time. So I can do, let's see, log-like. The first one was fit.plus, fit.negbin, zi plus. Okay, there they are. And this is also very helpfully showing us the number of degrees of freedom for each. So this is the number of degrees of freedom in the data after fitting all of the parameters of this model. Or sorry, this is telling us the number of degrees of freedom that we have consumed by fitting this model. So the Poisson model consumed 5 degrees of freedom. The negative binomial model, because it has 1 additional parameter to fit, the dispersion parameter consumes 1 more. The zero inflated Poisson, actually, why is the zero inflated Poisson doing 1 more? How did I fit these differently? Let me see. Poisson, negative bin. These look the same. Let me just fit those again to make sure. Make sure that's up to date. Ah, I had some that thing that happens when you're doing interactive data analysis where you change code without rerunning it. So this actually looks correct now that the zero inflated Poisson model consumes the same number of degrees of freedom as the negative binomial model, and the zero inflated negative binomial model consumes 1 additional degree of freedom. So this is just for the covariates and the value of lambda. This is covariates plus lambda plus dispersion. This is covariates plus lambda plus the intercept of the zero inflation model. And this is the same plus the dispersion of the count model. Of course, if I had fit the full zero inflation models like is the default, then these would have consumed much more degrees of freedom. Demonstrate a fancier way. Okay, this is, so I had in mind the lapply function. The family of apply functions in our apply, these are implicit loops. I used apply once to loop over the columns of a data frame. Lapply loops over a list. It basically repeats a function over either, with apply, it's rows or columns of a data frame or matrix. With lapply, it's elements of a matrix. So I can create a list, fit.plus, fit.negbin, fit.zi plus, fit.zi-negbin. And I can do lapply and log like. So what this is going to do is apply log likelihood to every element of this list. It's not named. It's going to be more informative if I actually name these. So I could call this plus, call this negbin, call this ci plus, and call this ci negbin. And here are all of these results. Maybe to make this a little bit clearer, I'll do it in 2 steps. Call this list of fits. So now this looks like this is a list object, and in each one there's this fitted model object. And then I can apply to that list of fits and calculate the log likelihood for each one of them. There's also an sapply function, that's simple apply, and it tries to convert this into a simpler object. In this case, since they're each of length 1, it can convert it into a vector. Probably though, if you want to do this kind of thing, it might be easier using the Broom package. I don't know, I haven't tried it for log likelihoods. I don't know if it's included in the Broom package, but I'll just stick with lapply. So I have these in 2 different code chunks. I'll put this here. Okay. To get an idea of how big a difference in -2 times log likelihood would be statistically significant on 1 difference of degrees of freedom, I can look at, here I'll look at the help page for Q chi-squared. These are the family of distributions. There's also a D, P, Q, and R for norm, for binom, for every distribution in R. This is for the chi-square distribution. Quantiles, Q is for quantiles, so you give a probability on the distribution and it tells you what the quantile is. So for example, if this was a normal distribution and you asked for the 97.5th, if you put Q norm, I'll just do it, Q norm 0.975, it's going to be 1.96. And if I did that for 0.025, it's going to be -1.96. So I'm just going to do the same thing here for the chi-squared distribution, Q chi-squared, probability of 0.95 with df equals 1. And actually that's equivalent to if I did it. So this is under the default is lower tail equals true. If I did it with lower dot tail equals false, that's going to look to the right hand tail, and it's the same answer. So that's telling me that this is the critical value for a difference in chi-squareds with 1 degree of freedom. And with 2 degrees of freedom, it's about 6. So those differences that I saw were on the order of hundreds. So those are obviously highly statistically significant. I don't even need to do a test or a p-value, well, to see that these far exceed this critical value. So it means that each of these additional degrees of freedom is, well, at least compared to the Poisson model, the negative binomial is producing a much, much better fit. And between the negative binomial and the zero inflated Poisson, actually the negative binomial is better. And if I look between the negative binomial and the zero inflated negative binomial, it actually doesn't look any better at all. That's a difference of less than 3.84. So based on this, I would probably just choose the negative binomial model. Okay, so I provided some functions here to help making residuals plots, since they're not supported by these by all of these packages, the PSCL and the mass package. And then I want to so what did I call that list of models again? I called it list of fits. Okay. Let's see, so I'll just try it with one of them first. Plot panel 1, list of fits 1, just to see what it does. So it produces this plot of predicted values versus residuals. This is the top left fit in the 4-panel plots that we did under linear regression. And plot panel 2 is the QQ plot. So let's see, what did this ask? Let's look at the plots, okay. Yeah, so this command will make 1 row and 2 columns. So just to show before I get into any looping, what this will do, it puts these two side by side. Now I'm going to make a loop for I in, let me see, I just need to test this, seek along, I think, list of fits. So that seek along is a function that just provides a sequence along the length of its argument. So seek along list of fits. And now I'll get rid of this 1 and make this I. And I'm going to add a title, main equals names list of fits I. I really don't have to do this loop here. There's only 4 of them. I could have just typed them all in here. Actually, I will. So now it says 4 rows and 2 columns. Poisson negative binomial, 0 inflated Poisson, and 0 inflated negative binomial. So even though we saw in the log likelihoods that the negative binomial is a better fit than the Poisson, the QQ plot still shows a lot of lack of fit in these high counts. So it's still way more over dispersed than the negative binomial. Okay. So next question. Plot predicted and observed counts. So in order to do this, I need to first get the get the predictions from each one of these models along with the observed. So for the observed, it is, I can take any one of them, fit dot. Actually, this is probably, wow. There are a few ways I could do this. One would be by using using the Broom package. So this is a little bit of a complicated problem just because we have 4 different models here. So the way I approached this was just to take the predictions from one of them. So for example, this $y are the actual observed values. And then I can do the predict fit dot plus gives me the predicted number of counts. And then I just built a, well, I could use in what's posted there, I used a Tibble, but it's really the same except for our purposes only the display compared to a data frame. Maybe I'll stick with a data frame this time and call it data.frame. Data.frame observed equals okay. So if I look at this, I've created a data frame that has the observed needle sharing counts for each participant and the predictions by each of these models. So then this is going to allow us to make this plot of observed versus predicted versus observed counts. Now, I could continue with base R here just as is. For example, I can do plot Poisson by observed data equals preds. And there's a scatter plot of the Poisson predictions versus the observed. But what I want to do now, I'm going to start with, I'm actually just going to make these as histograms. So that would look like hist of preds. Okay, so there's one way to make a histogram. I'm going to do this using a ggplot way. First, I'm going to do dev.off to turn off this graphics device since it was, I want to get rid of that parmf row thing that I had done. There's also Yeah, I could have also done that with the button up here. But the first thing I did here was pivot this into a long format. This is from the tidyr package. And this is just a good time to demonstrate this because converting between wide and long format data frames is a pretty common operation. Pivot longer. Maybe I'll take a look at the help page for that. The inverse transformation is pivot wider, so the data is PREDS. Then I need to say which columns I want to pivot. And I can use any of these things, and I just want to pivot everything. So I could also use it to pick only columns that started with something, ended with something, contain some string, match a regular expression, match some numerical range. There are lots of options, or specifying any of a number of options, just explicitly specifying them. I'm just going to do everything. So just to show what this looks like, it's now just a 2-column thing. So all of those values got turned into a single column called value, and there's a new column called name that says which it came from. And the thing that this gives me, well, I guess I can look at this here as summary preds.long. So for starters, I could do something like ggplot preds.long as x equals name, y equals value, plus geom, box plot. So ggplot works well with long format. So I can see here my observed and all of these predictions. And what you see is there's way more zeros in the observed, and there's also way more extreme values than with any of these. And clearly this, both the Poisson, but especially this zero Poisson really underestimates the number of zeros. That's kind of ironic. But now I'm going to do this again. Actually, this is a box plot. And now let's do this again with x equals value. And I'll make a bar plot. This is just going to make one bar plot. Sorry, what did I do wrong? Just geom bar. So this is, sorry, this should have been, that didn't work out at all. I'm going to try doing this correctly with the, so the faceting, there's a couple of faceting commands. There's a facet grid that lets you specify number of rows and columns, and a facet wrap, which I'm going to use, and I'll just show you what it does. what it does is separate this out by name. So it looks a little bit better now, except it's choosing kind of funny values for the continuous predictions. So I'm going to specify again a bin width. Sorry, I want a histogram. That's what, not a bar plot. There we go. So here you can see really this difference between the observed and all of these others. And I could change the order of this facet wrapping, one by creating a factor that had observed as the reference value. Let me see if there's another option. Yeah, so I could also I'd have to take a look at I'd have to take a look at the help page for facet wrap to remember how to change the position from the default. This is kind of the equivalent in ggplot to that par function that I used, but it's more powerful because it lets you. So facet wrap works on. Let's see. There's a different facet. So it wraps a 1D sequence of panels into 2D, which is generally a better use of screen plate space than facet grid because most displays are roughly rectangular. And facet grid forms a matrix of panels defined by row and column faceting variables. Most useful when you have two discrete variables. And all combination of the variables exist in the data. So I'm only wrapping by one variable, this name. So I'm using facet wrap. With facet grid, I could specify two different variables and put one of them on the rows and the other one on the columns. So in summary, we can see that none of the models come very close to modeling these extreme counts of 30 plus. This might require a more complex mixture model, such as a mixture of zero inflation plus two different count distributions, one with a much higher mean, maybe. I actually liked the suggestion we had earlier a lot, that there's just an important covariate missing, such as whether someone shares needles with a household partner. But this kind of multi-mixture model would be a way of representing a reality like that when we didn't have that household data, saying that we actually have two different count generating distributions, one for people who share needles with someone in their household, and one for someone who does not live with anyone else, and trying to infer that from the data without actually knowing who is who. All right, thanks. And that's the end of the lab.